webcam for now. Speakers here. And I'm just going to share the screen so they can see your slides, but hopefully hear your voice through the webcam. So hope that all works. And there you go. Okay, sorry. So that was Haley, that was 4 you asked about?
Yes.
A cart loaded with bricks has a total mass of so many kilograms. Pulled at a constant speed by a rope inclined at 24.7 degrees above the horizontal. Or your numbers will be different, but let me draw a diagram with my numbers here. So I've got 9.13 kilograms is my value for the mass. I'm just going to imagine that I'm going to put a nice round number there. There's some tension in the rope. I don't know what that is. And the cart is moved on the ground a distance of 15 meters, 15.1 meters in my version. And we're given the coefficient of kinetic friction between the cart and the floor is, I'm just going to say 0.6. Mine has 3 decimal places given. How much work is done by the cart, on the cart, by the rope? And in this case, well, we're in, this is chapter 6, so I might be able to calculate it by doing F equals MA kinds of stuff, but
I tried to do the sum of the forces in the X direction to get tension.
right, which is equal to 0 because it's not accelerating, right? It's moving at constant velocity.
Okay, right, yeah.
So that would be part of that, and then you could figure out the tension. That would be like something we did back in chapter 4, right? And then if you had the tension, you could do T times the cosine of 24 times 15.1 in my version of the problem. And that would give you the work done by the tension. Now, I think there's a slightly different way we could do it that's more chapter 6-like. You're still using the idea of work there, but suppose let me see if this works out. Let's apply this. Net work done by all forces on the cart is equal to the change in kinetic energy of the cart, and that of course is 0. So in this case, that would be the work done, well, gravity doesn't do any work, normal force doesn't do any work. The only 2 forces that are doing work are the tension, it's doing some positive work, and friction is doing some negative work. So I'm going to do W by friction plus W by the tension. Those add to 0. So I can kind of back this out. I could say this is what we want, right? How much work is done by the tension in the rope or whatever. If I could calculate this, this is just going to be the negative of that. So how much work is done by friction? Well, let's see. What's the magnitude? Well, first of all, it's negative work that's done by friction because friction is going back that way while it's moving to the right. So it's going to be negative work. The magnitude of the friction force is going to be whatever your mu kinetic was times the normal force. Oh, but the normal force I need to figure out by, it's not so obvious what the normal force is. And I guess maybe you're still confused because you're saying I did all this and I didn't get the correct answer. Is that right?
Kind of. I got stuck after I found the tension, but then when you told me to multiply by the distance, that made sense. So now I have the work by the tension.
Right. But the thing I wanted to make sure of is that you're not saying the normal force. You know, in order to figure out the tension, you need to figure out what the friction force is, right? Because that's part of the sum of the force x components equals 0. And the friction force depends on the normal force, and the normal force is not equal to mg in this case. Because again, it's a case where somebody's pulling up a little bit on an object, so they're reducing the normal force that the floor has to push up by to keep it not accelerating in the vertical direction. Are you okay with that comment? Like, the normal force is not equal to 9.13 times 9.8 in my numbers of the problem. you have to do the sum of the force y components equal to 0, and there are 3 of them that contribute there. The tension force has a y component, the normal force has a y component, and the weight force has a y component. The 3 of those add to 0, and that allows me to, well, maybe we should go through this in detail, or are you cleared up on it? Do you think, because you won't be able to solve for the normal force there, because the normal force is going to depend on the tension in this particular
But
problem.
if I did the sum of the forces of y components, I could get normal force that way. And then
Well, but that's going to depend on t, and you still don't know what t is. So we're going to need both the sum of the force y components and the sum of the force x components. Let's just work it out here. Let me turn this into a little free-body diagram. And since presumably at least Mongi is wondering if Noah's back, let me just share this since we're talking about a problem now with the Mongi. I'm going to turn this into a free body diagram. Here's one force on it. There's a normal force. There's a kinetic friction force. I'm just going to write that as mu k times the normal force. And then there's a weight force. Let's just call it mg. Okay, there's my free body diagram. If I do, and let's take the usual kinds of axes, horizontal and vertical. If I do the sum of the force y components equals may, it's not accelerating along the y direction. So these two forces would have positive y components. T sine 24 in my version of the problem minus mg equals 0. Now, I can calculate this in my calculator, and I know what the mass is, so I can calculate that, but I still don't know 2 things in that equation, right? So it's not, I can't figure out what t is from that. Let's go over to some of the force x components.
Hey, can you move the screen over a little bit? Because it's like out of frame a little bit.
Sure.
To the right.
To the right, okay.
Thank you.
Yeah, there. Good. All right. Some of the, and by the way, this is problem 4 in chapter 6, part 1.
Yeah,
Some of the force x components equals max. That's also 0 because it's moving at constant velocity, right? So the right-hand side is 0. Some of the force x components, there's only 2 non-zero x components here. I get in my coordinate system, that's t cosine 24 degrees minus mu k times the normal force. Those add to 0. And in this case, I know how to calculate this, and I know how to calculate this. But again, I don't know the normal force, I don't know t. So I've got 2 equations here and 2 unknowns. And I've got to do that process to solve, if you wanted to do it the way you were talking about, eliminate the normal force and just solve for t. And then once you've got t, you're just going to do g times the cosine of the angle times the distance to get the force, the work that force did. Is that enough on that one?
yes,
Okay. Great.
thank you.
No problem. All right, so let's get into our 5-minute presentation with Anna.
Wait, sorry, for this one, would you do substitute for, would you solve for one, like said, like choose one of those to?
Yeah, I want to solve for t, so I might solve this one, whichever one you solve for first is the one that's going to disappear in a substitution problem. So I might solve this one for Fn. Fn would be mg minus t sine 24. And then I substitute that in for Fn in parentheses over here, and then I would have an equation that only involves t. And then we go back to the very beginning of this chapter and figure out what, how to calculate the work done by that t by just taking fx times fx. All right, remember to unmute when you're ready, or video mute, I mean, and take it away.
Well, individuals on Zoom being able to see it, I'm not sure how to.
They should already be able to see it. I've got screen share on there. Is that right? Does it say?
Well, it's showing up the board.
Well, it always shows what's on the board, but it's actually sharing the screen.
Yeah, we can see it. You're good.
Yeah, you're good.
But I mean, unvideo mute it for us here in the room.
All right, hi everyone. My name is Anna, and today I'm going to share a little bit about the very, very basics of NMR spectroscopy, specifically the basic physics of NMR spectroscopy. So NMR spectroscopy is used to learn about the basic structure of organic molecules, and it has many different applications in scientific research, especially environmental science, which is a field I'm particularly interested in pursuing in graduate school. So I plan to become very familiar with NMR in the future. In order to learn a little about NMR spectroscopy, let me first break it down into its components. So NMR stands for nuclear magnetic resonance, which is a physical phenomenon of resonance transition between magnetic energy levels that occurs when atomic nuclei are surrounded by an external magnetic field and subjected to electromagnetic radiation of a specific frequency. The nuclei absorb and re-emit this electromagnetic radiation, which is important for creating a spectra, which leads to the second portion of NMR spectroscopy, which is spectroscopy. And that's just the branch of science that's concerned with the interactions between light and matter through analyzing spectra. And in this case, these spectra are graphs that show the response of molecular systems to different wavelengths of radiation. So one of the main individuals we have to thank for this revolutionary technique used in chemistry is physicist Isidore Isaac Rabi, who was an American physicist that won the Nobel Prize for discovering nuclear magnetic resonance in 1944. And specifically, NMR builds on two other concepts in physics, which are resonance and nuclear spin. So resonance is a phenomenon that occurs when an external force causes another system to vibrate at a greater amplitude. And then nuclear spin refers to the angular momentum of a fundamental particle of an atom. So fundamental particle, we can't get any smaller than that. This angular momentum is only exhibited by atomic nuclei with an odd number of protons or neutrons. And those with even numbers will not have any kind of nuclear spin. So for NMR spectroscopy, you would rely on protons, since they are singular proton, or carbon-13, since they have that odd number. And on this figure, this is a figure that I liked because it shows kind of the magnetic energy levels for atomic nuclei. The top one shows how the atomic nuclei would be spinning opposing the magnetic field. The external magnetic field, while the lower energy one on the bottom would be spinning with the magnetic field. So all of this is on the level of quantum physics, so it's incredibly complex. And on a very basic level, what's happening is that the absorption of radiation matches the nuclei's precessional frequency, which is referred to as the Lamar frequency. And this causes their quote-unquote spin to flip to a higher energy state due to being in resonance with the magnetic field. So as you can see from the GIF on the left, what I mean by precession is the nuclei spinning around that tilted axis. And then on the right, the figure shows what is meant by a flip, which is a change in spin direction of the nuclei. So then the absorbed and emitted energy during this process of flipping, because it is very energy intensive, can be measured to create a graph of unique signals for a molecule. So this is an example of a carbon-13 NMR spectrum of an unknown compound I had to try to identify in organic 1, which I ended up predicting to be 2-methyl-acetophenone from the spectrum signals of carbon NMR and then also proton NMR, which I don't have shown. Does anyone have any very basic questions? Yeah, Haley.
So I know in organic 1 and in organic 2, we kind of focus on like proton NMR a lot here.
Yeah.
Is that like different than the carbon NMR, or are they like the same mechanism? Do you know?
From my reading, they're basically doing the same kind of mechanism with nuclear spin. It's just focusing on a different frequency with a different, since they're different molecules.
How is this applied to thermal studies?
So what I've been reading recently is I'm specifically interested in pursuing aquatic toxicology. So it's being used a lot now and starting to develop more to try to identify certain compounds that are present within aquatic ecosystems. And also they're doing some really cool research on in vivo NMR spectroscopy to see how toxins are affecting whole organisms.
And is the carbon-13 just naturally occurring, or is that something you could build a sample with or something like that? You know, because
Should be
most
naturally
carbon is
occurring.
carbon-12, but there is a small percentage that would be carbon-13 in the natural environment. Is that, when you're doing environmental samples, are you just relying on what there happens to be randomly incorporated into things?
To be honest, I didn't fully refresh my memory on that. However, you do use a specific solution when you're doing in vitro, like NMR in the lab. So I believe that's kind of the mechanism they're relying on.
All right, thank you very much.
Sorry, was that like
Yeah, that was,
Yes. Okay, let me just switch things around here for the benefit of the exit full screen, X that out. Switch the microphone.
Dr. Kelly, I can't hear you.
Yeah, I can't either.
Now,
Yep,
can you
that's
hear me
better.
now,
Yes.
Noah?
Yep.
Good. Sorry, I didn't have I turned off my microphone because of the talk, and then I forgot to turn it back on. So yeah, the answer is yes, there are other examples of potential energy besides gravitational and spring potential energy. We're just not going to talk about them in Physics 110, but you know, we're just trying to have enough. We'll have kind of 3 different examples of these functions, and that gives us a variety of problems, but we don't want to exhaustively think about it. Hooke's law only works, it says in the book, if the x is relatively small. How can we quantify this? Is there a certain length? Well, no, it depends on the spring. But you can imagine, here's a real spring that I'm holding up in front of me, and this particular spring happens to be pretty tightly coiled in that, this part in the middle has someone stretched it out too far, and now it's stayed stretched out, so it doesn't really come compressed anymore. But this part over here, I can't really compress this spring. Once I get it, I'm stretching it right now. If I try to compress it, it's relaxed right now. If I try to compress it, the coils hit each other. And what that means is it's not going to behave like Hooke's law. To behave like Hooke's law, you've got to have a lot of region where you can compress and a lot of region where you can stretch out. But still, there are limits to that. If I stretch out this spring, I would ruin it if I did it. But if I just try to stretch it out as far as I could, and it's almost just like a wire straightened out, it's not going to go back to a nice spring after that. But once you get to a stretched out wire, all of a sudden, if you try to stretch it a little bit more, the force goes up by a huge amount. So it's not like Hooke's law at that point anymore. Now, how far I can stretch it depends on the spring. In other words, if I've got a really long spring with 500 coils in it, I can stretch it a huge distance before I really get to that fully stretched out wire kind of position. Whereas if I've got a spring with only 10 coils in it, I might stretch it this far, and it's already just a pure wire. So it depends on how big of a spring it is and details of it. But when we talk about a spring in this class, we're going to assume that for whatever region of stretching we're talking about, it still obeys Hooke's law, even though we know for a real spring, you have to be careful. And it depends on the details when that falls, when it's not true anymore. In the textbook, it says Hooke's law only works if the x, the amount, oh, sorry, we did that one. All right, so let's move on. Just to introduce a term that you saw in the reading, I believe, mechanical energy. So we've been talking about, just to review a little bit, we talked about 2 days ago, the net work done by, sorry, this shouldn't say by external forces, it's just the net work. We don't need the external forces. If we've got a particle, then the net work done on it between some initial and final state is equal to the change in kinetic energy. That's the work kinetic energy theorem, or sometimes it's called the work energy theorem. Here's another work energy relation that we were using a lot yesterday. The net work done by external forces is equal to the change in kinetic energy plus the change in potential energy. Sometimes people take kinetic and potential and add them together, and they call that collectively mechanical energy. So you could have more mechanical energy by bits of mass in your system moving faster, or by springs being compressed a lot at a certain period of time, or being stretched a lot. All of those would contribute to mechanical energy. And sometimes it's useful to think about what this is saying about changes in mechanical energy. So if there are, as we saw often we choose a system so that there are no external forces doing work. What this is saying is then the change in mechanical energy is 0. Sometimes people will call that, when the left-hand side is 0 in that second relation, when delta KE plus delta PE equals 0, they will say mechanical energy is conserved, or that equation is the conservation of mechanical energy. And conservation means when you're going from initial to final, something doesn't change. When something doesn't change, it's conserved. So you might have a situation where mechanical energy is conserved. So for example, if I take a mass and I toss it up in the air, so right when I release it and it's going up, it's not touching my hand anymore, I would say at that point, the kinetic energy is very large, but it doesn't have so much potential energy. It's going to increase in potential energy as it goes upward, right? So as the mass goes upward, its kinetic energy gets smaller, 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 smaller. But simultaneously, its potential energy is getting bigger and bigger and bigger. Not its potential energy, but the potential energy stored in the system consisting of the mass and the Earth, where gravity is an internal force. So we can, sometimes think of problems in terms of changes in mechanical energy. So there's an example, ball tossed straight up. What's going on is when mechanical energy is conserved, you're just changing out between potential energy and kinetic energy. So however much the potential energy goes down, the kinetic energy goes up. And that allows you to figure out what some final velocities might be, for example. Same thing can be true for springs. If I have a mass attached to a spring, we did an example like this yesterday, and the other end attached to an immovable wall, and I compress it and let it go, that's my initial, and maybe final is when it's passing the spring's relaxed position. At that point, the mass is moving a lot. My initial state, I would have a lot of potential energy, right? I've compressed that spring, but no kinetic energy because it's released from rest. And then it decompresses, the potential energy goes down and the kinetic energy goes up. And as it's passing equilibrium, there's no potential energy left, but now there's a lot of kinetic energy. The idea is the sum of them stays constant. Okay, so I'm skipping over a lot of the words that I spent more time on when doing these videos. Here's a couple of examples that were in the videos, but worth talking about. So here's imagine a frictionless bowl. This is supposed to be a hemispherical bowl, but this is just a side view of it, and an ice cube. So it slides down without friction. If it's released from rest at the very top of the hemispherical bowl, how fast is it going when it zooms by the bottom? And again, I would like to use the conservation of mechanical energy, but I've got to be able to choose my system very carefully. I can't say mechanical energy is conserved if I'm choosing just the particle. So in this case, I'm going to take the system to be just in the same way we ignored in one case where we had an object on an inclined plane and gravity was acting. I said, let's take the system to be the object on the plane plus Earth. That internal gravitational force we'll take to be an internal force. But let's imagine we'll treat the plane as an external force that's reaching in from the outside and doing some more pushing on parts of the system. Here it's the same way. I'm going to take the bowl to be an external force. In other words, my system is the ice cube plus Earth. The gravitational force between them I'm going to take to be an internal force, but the force from the bowl is some intervening external force. Again, it's my choice as to what the system is, but I'm trying to, we'll go over some rules of thumb for what might make choosing the system a little bit easier after we're all done with this. In that case, when I calculate the net work done by external forces, the only external force that is acting on a moving part of the system is the bowl force. There's no friction force, it's just a normal force that's from the bowl. And it's always perpendicular to the direction it's going. In other words, when the ice cube is here, 45 degrees down, the ice cube's going parallel to the surface, and the normal force is always perpendicular to the surface. So that normal force is doing zero work. That often happens when something's sliding on a surface, the normal force, even if the surface is curving, the normal force is always doing zero work because it's perpendicular to the direction of the velocity. And so even though I do have an external force, this left-hand side is zero, and that means mechanical energy is conserved. So this side is zero because it's because the normal force is doing zero work, and therefore I can solve for what the final velocity is using techniques very similar to what we did before. It's not a very enlightening answer, but it just illustrates how choosing the system can make things rather simple sometimes. Okay, there was a little lie or an error of omission, I might say, in what I told you earlier, and that was I left it out on purpose just to make things not seem so complicated all at once. But at some point, this thing that's circled in yellow over here, I said, well, what are we going to do to figure out a relationship between some work done by external forces and changes in energy in the system in the case where there are some internal forces? And the answer was, well, we could always imagine that all the forces were external, do it the old-fashioned way, but we're going to separate them by forces that we want to call internal and forces that we want to call external. We'll put all the internal forces on this side with a minus sign, and we'll just redefine that. Whatever is minus the net work done by internal forces, we'll define that to be the change in the potential energy of the system. That seems harmless enough. It's just a definition. But you'll see it doesn't make sense. In other words, does it make any sense to always say that the change in potential energy is equal, can be defined to be the negative of the work done by internal forces? In other words, the final potential energy minus the initial potential energy can be defined to be that. The answer is it doesn't always make sense, and that's because the work done by a force depends on the whole process of getting from the initial state to the final state. Whereas the left-hand side of what I've got shown here only depends on what the initial state and the final state are, but it, of course, doesn't know anything about how you got from initial to final, right? I'm saying, calculate something in the final state, subtract something calculated in the initial state. Who cares how you got from initial to final? But the right-hand side might depend on how I got from initial to final. Let me go back to the camera and maybe, I'm not sure how I can demonstrate this with the camera, but let's imagine this mass is on a table just so I can stand in front of the camera, sliding around on the table like this, right? As, let's say, the initial state is right here and at rest, sitting on the table, right? Final state's going to be over here and at rest, okay? There's friction between the mass and the table. So let's imagine I'm concerned by how much work that friction force does on this mass as it gets from there to over there. One way I could get it from initial to final is just to slide it straight over in that direction. And the friction force would do a certain amount of negative work in that process, right? So it might do a small amount of negative work because friction force is always pulling back and it's moving forward in this direction. Another way to get from the initial state to the final state would be to have it start moving around and go on a really tortuous path. Now, the whole time it's going on this path, friction is always pointing in the opposite direction to where it's going. So friction's doing more and more negative work as I'm winding around. And if I take a really long path and then finally end up at the same final position that I intended to end up at, the amount of work that's done by friction could be huge in that case. Huge and negative is what I mean. So it doesn't always make sense to do what I sort of, passed over without comment earlier on, of defining the change in potential energy. That means something that only depends on the final state and the initial state to be equal to the negative of the work done by internal forces. If one of my internal forces is like friction, at least, it seems like we might be in trouble. Okay, so in general, the answer is no. But for a lot of kinds of systems or kinds of forces, it actually doesn't depend on how you get from initial to final. And those forces you read about were called conservative forces. Gravity is an example of a conservative force. Let me just give you a couple of examples about how this might be the case. So the claim is, let's say my initial state for this mass is down here and at rest, and the final state is up here and at rest. And let's go through the same process and try to convince ourselves that it might not depend on how I get from initial to final. So one way I could get from initial to final is maybe my hand is a different force, but we're concerned with the work that gravity's doing. So I grab it with my hand, I bring it up there and bring it to rest. Gravity does a certain amount of negative work during that process. Would everyone agree with that? Because gravity's pulling down on it and it's moving upward. So that's a little bit of negative work. Now I'm going to try to do a similar process to what I did before with friction. And that is, I'm first going to say, let's start at the initial position. Let's go down. Gravity does a little bit of positive work. Then I'm going to go horizontal. How much work does gravity do there? 0, because it's perpendicular to the direction it's moving. Then I'm going to go back up to the same height that I started at. What sign work does gravity do there? Negative. In fact, however much positive work it did on the way down over here, it does just as much negative work coming back up to there. Now I'm going to overshoot where I wanted to end up at. So gravity does a whole lot more negative work. Then 0. Then I come down to where I wanted to end up at, and gravity does a little bit more of positive work. When you do that, the amount of work that gravity is doing doesn't depend on how crazy of a path I took from initial to final. The positives are always going to cancel out the negatives and give you the same amount of work, whether you went straight up there or took some really tortuous path. So gravity is what we would call a conservative force, and it does make sense to define that to be equal to the change in potential energy of the system, where gravity is an internal force in that case, because the work done only depends on where you started and where you ended up. It only depends on the initial and the final. That was the problem. The same thing's true of a spring force. You might say, maybe I've got a mass. I don't have one of my masses, but imagine this hand has a mass in it, and this hand is the wall or something like that. And I might say, Well, let's look at the spring force. The spring's relaxed. I use my hand to pull the spring out like this. The spring force itself does what kind of work? Positive, negative, or zero? Going from here, initial is here at rest, and final is here at rest. And my hand is holding a mass, let's say. It does some negative work because it's pulling on the point where the force is attached to this mass. It's pulling in the direction opposite to the direction of motion. So it does some negative work. So again, just like the gravity case, let's imagine that I first, instead of going directly there, I start at the same initial point. I compress the spring a little bit. Is the spring force doing positive, negative, or zero work there? I'm actually pushing it together with my hand. Now think about not my hand force, but the spring force. Which way is the spring force pushing? I can't point, but it's, yeah, that way. So I pushed it in this direction. The spring force is pushing in that direction. So that means the spring force is doing negative work. Then maybe I bring it up here. Let's just stick to one dimension in this case. Then I bring it back. It does some positive work again. Now I'm back to where I started. Now I overshoot. It does too much negative work. And then I go back to where I intended to end up at, and it does a little bit more positive work. So you can think about it. I mean, I know this is an inexhaustive proof, but in this case, the amount of work that's done by the spring force as I go from some specified initial state to some final state doesn't depend on how you got there. And therefore, that redefinition, and I know this usually is one of the most complicated things to sort of think about, but the book talks about it, and we normally talk about it here. So when we're doing this derivation, we can only bring that work from an conservative internal force over here to the other side with a minus sign and redefine it to be a change in potential energy if that force is a conservative force. Okay? So how we're going to deal with this in general is, suppose we want to put a force into our system and make it an internal force. So I'm going to break things up even more before. Remember before I said, let's divide it up into external and internal. Well, now some of my internal forces might be non-conservative, so they might cause problems. And other ones might be conservative, so they're good. So I'm going to break up the internal forces into non-conservative, that's the NC over here, and conservative parts. Those are both internal that are shown in green over here. For the conservative ones, I'm certainly welcome to bring that over to this side and make that redefinition in terms of a change in potential energy. But it makes absolutely no sense to do that with the non-conservative ones. So what we're going to do is, if you insist on making some non-conservative force, and we'll talk about what forces those are, if you insist on making it internal, even though we said we were going to try to leave just external forces on the left-hand side of these work-energy relations, if you've got an internal non-conservative force, we're still going to leave it on the left-hand side. We're only going to bring the ones over to the right-hand side and write them as a change in potential energy if they're conservative forces, okay? So here is yet a third work-energy relation that sort of teases this out. And let's go back to sort of the high-level picture. Well, I guess we will in a second. Let's talk about examples first. So what are conservative forces that we're going to be dealing with? Well, the only ones we really care about are gravity, conservative, and spring Hooke's law forces are conservative. And that's important for us because we already gave the potential energy. It wouldn't even make sense to give a potential energy function for a force that's not conservative. There is no such thing as a potential energy. But as we talked about electric forces, there is an associated potential energy. That's a conservative force as well. The magnetic force is a little bit weird because magnetic forces never do work. But that's a different story. What are the classic non-conservative forces? Well, they're things like friction. We already found out friction. It depends, the amount of work that's done by friction depends on how you got from initial to final. And air resistance is kind of like friction, right? It just pushes back along the direction you're moving. So the longer your path is, it doesn't matter how close initial and final are, the longer your path is, air resistance is always going to be going in the opposite direction. It's going to keep doing more and more negative work. So these kinds of forces, if you put them in your system, you can't really change them into a potential energy. You just have to directly somehow calculate the work. My recommendation is always going to be, if you have a friction or an air resistance force, always leave them external. And that way they'll always appear on the left-hand sides anyways. Okay? So if you've got these, sure, what we said before is only true if your forces are all conservative. If you've got some non-conservative forces, you've got to leave those non-conservative forces on the left-hand side. The easiest way to do that is just to make them external to your system. So, you know, if we've got an inclined plane and there's friction with the inclined plane, let's make the force from the plane on the object that's sliding an external force, both the normal force and the friction force, and then it will automatically appear over on this side. Okay, and the problem with these non-conservative forces that appear on the side is we have to be able to calculate the work directly there. And sometimes the amount of work that's done will be given in a problem. And for each conservative internal force, we have to know the associated potential energy function. We've only got 3 examples of those. Okay, let's try, I think this is the rest of that worksheet, which looks like a lot there, but let's look at the worksheet down to exercise 11. So I'm looking at the wrong worksheet here. The same interminable worksheet that we've been working on for so long, which is this it here? Yes. Problem 11. Let's look at 11 together, and then I'll leave you to do 12 and 13. Half-kilogram ball is launched upward at 30 meters per second initial speed. Let me show the board. And suppose the ball rises to its maximum. As it rises, someone just tells us, I don't know how they knew this, but they somehow know that the air resistance does minus 50 joules of work. Hopefully that minus 50 is not surprising. At least it should be negative, right? As the ball is rising, the air resistance force is pushing against the direction it's going, so it's doing some negative work. The question is, find the maximum height to which it rises. Okay, so since I've got a non-conservative force, I'm just going to try to put that external to my system. If I've got a conservative force, I can either make it internal or external, but you know, we're used to using potential energies now, or we're getting used to it, so we might want to make that internal. So in this case, for problem 11, I'm going to take my system. It was a ball, so we'll say ball plus Earth. The gravitational force is internal, but air resistance is an external force. And I think gravity and air resistance are the only forces that are actually doing work on the moving parts of this thing as it goes from the initial to final. Okay, so let's see what we know. So I'm going to take initial to be right after it's launched, and final to be when it rises to its maximum height. Okay, that's what's going to define initial and final here. And let's do the net work done by external forces is equal to delta KE plus delta PE. What's the left-hand side going to be here? Yeah, it was just given to us. We didn't really have to work for it, but we were told the net work done by air resistance force on the ball is minus 50 joules. So it's doing some negative work on it as it rises. The right-hand side, oh, I just go into brainless mode now, right? 1/2 mv final squared minus 1/2 mv initial squared. And we made gravity internal, so I need to use the associated potential energy for my system consisting of the ball plus the Earth, where gravity is an internal force, and that's mgy, right, where plus y is up. So our potential energy function is going to be mgy, where m is the mass of the ball that we're talking about. So plus PE final, so that's mgy final, minus mgy initial. And I'm going to do the same thing that I've done several times yesterday. Let's just factor out the mg. y final minus y initial. Because I think we're asked here for how high up does it go, right? What's its maximum height above the launch point? This is what I'm after, right? I might even more compactly write this as delta y. That's the variable we want to solve for. Now notice in this case, delta KE plus delta PE is not equal to 0. So I would say this is a case where mechanical energy is not conserved. On the way to going up to the top, we lose a certain amount of potential energy. We lose a certain amount of kinetic energy, but we don't gain as much potential energy back because it's not going as high as it would have if there were no atmosphere there. But in any case, I can just now plug in the numbers. I know everything in this problem. I know the mass of the ball. I know the final velocity is what? 0. That final velocity is 0. Initial velocity was given, mass of the ball was given, got the mass of the ball, so I can solve for delta y there. So this was a case where I'm not sure how this person knew that minus 50 joules of work is done, but in that case, I could calculate how far up it goes. And I get 35.7 meters when you run it through here. Okay, try 12 and 13. Both of these are not long extended problems, but they almost sound very similar to each other, but they end up being a little bit different. In both cases, something is given an initial push on a table with friction. It starts slowing down as it slides along the table.
Anybody having trouble getting started? Do we need to kick start it together? Most people seem like they're working happily, joyously. Put my answers up on the board, so check yours when you get there. Okay, let's look at 12. There's not much of a calculation. You know, the hardest part of this is thinking about it, deciding on your system, and then thinking about what your variable is going to be. A 2 kilogram block is given a 3 meter per second initial push on a rough horizontal table with a given coefficient of kinetic friction. And, you know, it comes to rest. I don't have enough table over there, but the idea is you're giving something a push. So my initial was just after the push. Final is it's come to rest. How much work is done by friction? Well, the first thing I think of always is, what's the sign of the answer that I'm expecting in this case? Negative, because friction's pushing back as it's going in one direction. It's pushing back or pulling back in the other direction. So I'm expecting a negative answer. So let me ask you, what do you want to choose for the system here? What about the friction force? Do I want to make that internal or external, do you think? I want to make it external because there's no associated potential energy that I can use. So it's going to appear on the left-hand side anyways. Why not just put it in with the external forces? I also know there's a normal force and a weight force that are acting as it's sliding along the table. I may as well make those external too, because I know they're not going to do any work anyways, right? Normal force isn't doing work. You know, weight force isn't doing work as it goes along. So let's make everything external. When you have an object, just a solid object, and every force acting on it is external, we're talking about treating it as a particle. So this is a good old work kinetic energy theorem kind of application. I don't even have to say the net work done by external forces. I'm going to say I guess I should be specific. My system is going to be, what did I call it here? A block? Yeah, just the block. My block's a particle. So I can use the good old work kinetic energy theorem in this case. There are 3 forces acting as it's sliding along: the friction force, the weight force, and the normal force. The weight force and the normal force do 0 work. So the net work done by all forces is just the work done by friction force. Okay, plus 0, plus 0. Those are for the normal force and the weight force. And that's equal to 1/2 mv final squared minus 1/2 mv initial squared. And v final is 0. So I put in my v initial. I put in my m. It's just negative 1/2 mv squared. That's what the work done by friction is. And it should be negative. Questions on that one? You know, calculationally it's simple. That doesn't mean conceptually it's simple. What about 13, which is the same kind of setup? A 2-kilogram block is given a 3 meter per second initial push on a rough horizontal table, same coefficient of kinetic friction. Find the speed of the block after it's moved 1 meter. I guess I should ask the question, we didn't use mu k in this answer. So what would happen if I made mu k really big or really small? What would we see in the difference? So here's my block on the table. I have a pretty big mu k, let's say right now. A lot of friction. And that's what happens. I push it at 3 meters per second. It comes to rest right there. Supposedly, this answer doesn't change if mu k is really small. What are we going to see if mu k is really small and I give it the same initial push over? It's going to go way over there, right? The claim is the same amount of work is done by the friction force. In one case, I had a big friction force multiplied by a small distance. In the other case, I had a smaller friction force when mu k is smaller, but it's going to go a bigger distance, and the two multiply out to give the same number. So it didn't depend on mu k. In any case, in 13, we have the same one, and we're asked a slightly different question. Find the speed of the block after it's moved 1 meter. Well, the situation hasn't changed. The forces that are acting haven't changed. So it seems like I'm still kind of motivated to choose my system to be the block, the particle, and I could still use the work kinetic energy theorem, the simplest of all these work energy relationships. I'm going to take initial to be right after release, seems to make sense, and final to be after it has moved 1 meter. It's still moving, hopefully then, otherwise the problem wouldn't make sense. It's sliding past 1 meter. When it was moved 1 meter, that's going to define what I mean by final. So let's try to fill this in. Again, there's a normal force, there's a weight force, there's a friction force. The other two are 0. So all I need to put in on the left-hand side is the work done by friction. I'm just going to sort of expand this out a little bit more at every step. 1/2 mv final squared minus 1/2 mv initial squared. I'm after v final. That's what we want to know here. What is the speed of this object after it's moved 1 meter? Now, I'm sunk if I don't know how to calculate this. Do we know how to calculate the work done by friction? Because I certainly know the mass, and I know v initial in this case. If we know how to calculate the work done by friction, we're in good shape. Yeah, we do it the good old-fashioned way, right? Fx delta x, and in this case, fx is going to be negative. If it's moving the plus x direction, then fx is going to be negative. So it's going to be minus, the magnitude of the friction force is mu k 0.3 times the normal force. In this case, the normal force is equal to the weight force, right? If I've got mg going down, and I've got a normal force there, and I've got a friction kinetic force there, these two have to balance out if it's not accelerating vertically, right? So this is mu k times the normal force. The normal force is mg. Okay. That's the magnitude of the friction. This is our fx. If it's moving in the plus x direction, this is our fx. And then I need to multiply by delta x to calculate the work done by friction. In this case, in between initial and final, it's moved 1 meter. Okay, that's equal to 1/2 m v final squared minus 1/2 m v initial squared. Now all I need to do is solve for v final. I guess the answer doesn't depend on the mass, right? It looks like I've got a common factor of m on both sides. And so the speed isn't going to depend on the mass. And you put the numbers in. In this case, I get 1.77 meters per second. Slowed down a little bit from its 3. So again, always check your answers, right? I pushed it at 3, it's slowing down, now it's at 1.77. If you got 36, you should check your work. Questions on those two? Both. I guess they're sort of going back to work kinetic energy, but at least thinking about friction doing that negative work, and I'm putting it on the left-hand side here. Yes?
Why can't you plug in the
Yeah, so in the previous problem, why couldn't I just calculate the work done by friction directly using this method? The question is, why didn't we do that in the previous problem? Somehow I didn't use the mu k, so I found out using my method that it didn't depend on mu k. The amount of work done by friction was the same no matter whether it slid a long distance or a short distance. If we did it this way, it seems like it would depend on mu k. So why can't we calculate it this way in the first problem? Oh, for the second one? Somebody help answer that one. Why can't I use the answer from the previous one in the second one? Yeah, we're asking for the final state is after it's moved 1 meter. Now it's still moving then, it hasn't come to a rest. So friction still is going to have done less than minus 9 joules in magnitude, right? It's going to be like -3 joules maybe by the time it passes 1 meter. It's still got some energy to lose. Good, any other questions? All right, we're getting close to the end. Now there were some other questions. I think we're supposed to do the next one together, if I remember correctly. And then I'm going to give the guidelines for choosing systems in just a second. Okay, so in 14, it says use energy methods. A box on an inclined plane is given a push downwards and slides with friction. Again, this sounds like a kind of problem that we could have done with kinematics and F equals ma back when, but let's use energy methods. Inclined plane, the angle is 40 degrees. Let's draw a little cartoon. 40-degree inclined plane. Here's a box. It's given some initial push on the plane. I'll say V initial is 0.75 meters per second. And it's after it slid 1.5 meters down the plane. So here it is at a later time. It's moved down the plane. This distance, the front of the box has moved, is 1.5 meters. And the question is, find its speed there. So I might say V final equals question mark. That's the setup. And we're given that the coefficient of kinetic friction is 0.25 and the mass is 2 kilograms. Trying to put all the information. 0. Okay, you help me think about what I might want to put in my system or leave out of the system, including the forces and the pieces. Say the block what? We could put them all in. Now I'm going to tell you up front a problem with putting them all in, is that you might have to leave out some forces in there. There is a force between the block and the ramp. Part of that force between the block and the ramp is a friction force, right? Those are forces they're exerting on each other. And that friction force is a non-conservative force. So I'm going to have to sort of leave it out of the right-hand side. There's no potential energy that's associated with a friction force. So I'm going to have to leave it out and calculate it directly on the left-hand side. So I'm kind of motivated to leave any non-conservative force out of the system. And so I would like to leave it out. I'm also going to, say the normal force. I kind of want that to be from outside the system too, because it doesn't do any work anyways, right? The normal force is always perpendicular. So I'm happy to calculate the work done by the normal force. It's just 0. So I like your suggestion, but I'm going to overrule in this case. And you could think about how you would do it. You'd still have to leave the same stuff on the left-hand side if you put it all in the system. So I'm going to take the block plus Earth is my system, Gravity is internal. The normal force and kinetic friction are external. And now I'm going to use my work-energy relationship. I don't have any internal non-conservative forces. The only non-conservative force I chose, I left it as external. So I can just use my old one I was using before, which says W net by external forces is equal to delta KE plus delta PE. And let's see, what are we asked for here? Well, the final speed? Okay. So let's think. My external forces are the normal force, it does 0 work, and the friction force, it's doing some negative work. So I would say, I could break this up. This is all external forces. The normal force does 0, so I'll put a little 0 plus there. And I'll say the work done by the friction force on the block. Okay, we're going to have to work on that a little bit more, but I'm trying to whittle it down here. And let's expand out the right-hand side. 1/2 mv final squared minus 1/2 mv initial squared plus, well, let's see. I made gravity an internal force. The gravitational potential energy always assumes plus y is up, and the potential energy formula is mgy. So that's going to be mgy final minus mgy initial, and as usual, I'm going to write that as mg times y final minus y initial, because that's how far it went down in y, right? We're going to have a negative y final minus y initial because it's gone down in y if plus y is up. All right, how am I going to calculate? So what are we after here? We're after V final. So I'm given the mass of the object. So I know this mass. I know V initial. I know this mass. I know G. Things I'm not really sure about so far is what is the change in the y coordinate? In other words, what is delta y? Well, first of all, it's negative, right? Delta y would be positive if you went up and plus y is up. Delta y is negative because it's actually going down closer to the surface of Earth. In this diagram right here, you could envision delta y like this. This is the magnitude of delta y. Delta y is negative, but this distance is the absolute value of it, right? If it goes down by 1.5 meters, the question is, how far does it go down just in terms of its y coordinate? That's what that means, that y final minus y initial, if plus y is up. And how would I figure that out, or how do I calculate that here? 1.5 sine 40, because if this is 40 degrees, this is also 40 degrees in this triangle right there. Okay, now let's be careful about signs. Remember, this is negative. The length of that vertical side is 1.5 times the sine of 40 degrees. But the change in y coordinate has an additional minus sign in front of it. Okay, so we got that. This is taken care of. So now I need to worry about this. How much work is done by friction as it moves down the plane there? Positive, negative, or 0? Negative. One of the reasons it's so good to ask yourself that is that it's easy to forget the sign of these things. You might just calculate the magnitude of the work and then forget about it. So as soon as I know it's negative, I put that minus sign there to be a placeholder for me. Okay, so what do I need? To calculate the magnitude of the work done by friction, I need the distance it moved. Do we know that? 1.5 meters, right? And I need the magnitude of the friction force. And I do know that, right? That's mu kinetic times the normal force. And I know mu kinetic is 0.25, so I've reduced it down now to, can I find the normal force? What do I do to find the normal force? Yeah, I need a free body diagram to figure it out, or if you can do it in your head, you're better than me at this kind of thing. 2 kilograms. So I've got a 2 times 9.8. I've got a normal force here. I've got a friction force here. And since I'm interested in the normal force, it seems reasonable, as this thing's going along, let's choose plus x to be along the plane and plus y. You don't have to call it plus y. I know it's a different plus y that's up there. We could call this z if you like. In any case, I'm going to do the sum of the force z components equals MAZ. And what is AZ? How fast is it accelerating along the z direction? Zero, because its z coordinate is staying constant as it slides down the plane, right? I hope you're not off put by the fact that I called it z and not I just didn't want to, my y meant something different up there, so I just changed what variable I was using. So if I do, this is a side calculation to figure out what the normal force is. We need that right there. Sum of the force z components equals MAZ. Okay, AZ is 0. This has a non-zero z component. It comes in with a plus sign, so that's just the normal force. And then this one over here, the usual business, this is 40 degrees here. So I do 2 times 9.8 times the cosine of 40 to get this side of the right triangle, which is the z component. Minus 2 times 9.8 times the cosine of 40 degrees. Okay. Let's put it all together. Minus mu k, 0.25, times the normal force. The normal force from this is equal to 2 times 9.8 times the cosine of 40 degrees. And then we got to, that was just the magnitude of the force, then we got to multiply by the distance, the 1.5 meters. That's equal to 1/2 times m, that's 2 in this case, times v final squared, minus 1/2 times 2 times v initial squared, and that was 0.75. It's being squared there. Plus m, that's 2, times g, that's 9.8, times minus 1.5 sine 40 degrees. It's not my favorite bit of algebra, but it's not so bad. The hardest part was right at the beginning here. And then I've got to solve for v final. And I get, according to my notes here, 3.72 meters per second. After you take the square root. Okay, that might make sense. So, it's sped up a little bit, right? I gave it an initial push. There is some friction. Friction could be so big that it's actually slowing down, but in this case, friction's not very big, and gravity's winning out over it, and it's actually speeding up as it goes down, but maybe not speeding up as fast as it would have if there were no friction. That's about as complicated as they're going to get, that particular problem. So, any questions on that one? All right. As promised now, let me just go over, now that we've seen a lot of examples, and before we do a brief just discussion of power, which is the last topic, and it's not very long, let me just talk about these guidelines for choosing the system. That seems like the whole confusion here is there's too many ways to choose the system. So we're going to use, some of these more complicated, perhaps, work-energy relationships. Andre. Here? Yeah. It's because we're calculating a work. We're going to, remember our good old thing we did very at the beginning of this chapter. The work done by a force is equal to Fx delta x. And it's that delta x, right? The rest of it is just the magnitude of the friction force, right? And it's, if If we call x plus x the direction it's moving, then it's a negative force x component. Good question. Sometimes it's hard for, I know this is like an overload, this chapter, and it's a long class that we go through every day, but it's good to see that people are checking the details. Okay, so first of all, how do I decide what to put in my system and outside of the system? If you don't know a potential energy expression for some force, well, if you put it in the system, it's going to appear as a potential energy on the right-hand side. So if you don't know a potential energy, make it external. Maybe there's a force from a hand, and I have some way to calculate the work that's done by it, but there's no potential energy I know associated with the hand force. So if there's something pushing it with a hand, I'm going to make that force external to my system. I'm only going to want to put in things internal to the system for which I know a potential energy, and that's only gravity and spring forces. So there's not too many choices there. All forces that are not gravitational or spring forces, make them external. Similarly, if you've got a conservative force that's non-constant, then you can't use this Fx delta x formula to actually explicitly calculate the work done by it. So I don't want it to appear on the left-hand side of one of these work-energy relationships because I don't know how to calculate that work. Hopefully, I've got a potential energy expression that somebody's handed to me from on high that came from calculus to put in. So if you have a non-constant force, put it in and hope that you have a potential energy expression to use. Okay, and finally, if the force is non-conservative, you're going to have to leave it on the left-hand side of your work-energy relationship anyways. You may as well put it external to the system because we're used to putting stuff over there anyways. If you make it internal, there's no way to use a potential energy function, so we're going to have to kind of awkwardly leave it on that side anyways. Why not make it external to the system, and then I don't have to worry about the two things being added together on that side. Okay, so those are the overall kinds of, if you go back and look at these kinds of problems we've been doing, I mean, I guess the other, the one other one I would add to that is, if you've got a simple object with simple forces acting on it, sometimes you can just go ahead and use the work kinetic energy theorem like we did for the simple horizontally sliding mass. That seemed like the easiest way to do that was work kinetic energy. All right, any questions on that beyond, hey, we've done a lot of examples, but we probably need to do a lot more examples before you're comfortable with choosing systems and calculating things on the left-hand side and the right-hand side. All right, let's go back. These were a little bit out of order, so I actually had to speed ahead here. But there was a discussion of power, the last topic, and it's not a long one. I had sort of a long-winded discussion of examples here associated with power. But let's just hit the high points and maybe do one example where we can go over the example that was in the slides here. When a force does work, there's a question of how long it takes to do that work. So for example, here's a force, my hand. I'm going to do some positive work with it by pushing in the same direction that this object is moving. So my hand is doing positive work on the mass that I'm raising, okay? Now, I could do the same if let's imagine that I'm raising it very slowly. And so as it raises up 1 meter, I do a certain amount of work. Well, if I'm raising it at constant velocity, my hand force is actually exactly opposite the weight force because the acceleration is 0. Doesn't matter if I'm moving it rapidly with 0 acceleration or slowly with 0 acceleration. My hand force would just balance out the weight force. So my hand force, whether I'm moving it quickly or slowly, is exerting the same amount of force as long as I'm not accelerating it. And it's moving the same distance. Let's imagine in both cases we move it up 1 meter. In one case, I happen to be raising it really quickly and we watch it as it moves up 1 meter. In another case, I'm moving it really painfully slowly and we watch it as it moves up 1 meter. The same amount of work is being done by my hand in both cases, but I'm doing that work at different rates. In one case, I do that amount of work really fast, and in the other case, I'm doing it slowly. power is measuring the rate at which a force does work. And so, well, maybe I can go to the slides. Everything I want to show is probably on there. So it's the rate at which an external force does work on a system. A lot of times that system might be a simple particle, but if it's got a lot of parts to it connected by springs or springy forces, a single force might be grabbing into one of the masses that's connected by springs and pushing it for a certain distance. And the question is, what is the rate at which work is being done there? Different books phrase it different ways. Sometimes they say a force delivers a certain power to the system. The power is the rate at which work is being done. Sometimes they'll say the force outputs a certain power. And sometimes which word is chosen depends on the context. The SI unit for power is watts. That's short for joules per second, right? So we're going to calculate a power by how much work is done divided by the amount of time it took. That's the rate at which it's being done. So joules for work divided by time in second. Joules for second, but it's so common that there's a shortcut unit. Watt means joules per second. So when you see, 1,000 watts on a hairdryer or something like that, that's a rate at which power is being delivered to that. The higher the wattage, the greater the rate at which power is being delivered. Positive power means that whatever force you're talking about is doing positive work as time goes on, whereas negative power is that force is doing negative work. So for example, I would say as I'm taking this mass and raising it up, my hand force is delivering positive power to the system consisting of this mass, or to the system consisting of this mass plus the Earth, where gravity is an internal force. Doesn't matter if it's a complicated system or not. My hand force is doing positive work. I'm pushing up and it's moving up. I'd be doing delivering greater power if I lifted it up faster, but in any case, it's positive. Whereas I would say I'm delivering negative work to the system if I lower it down closer to Earth. Or, another way to think of it is you could think of the mass force as, that downward force that's exerting on my hand, is it's delivering power to me. Another way we phrase that is saying I deliver negative power to the system. That means it's delivering power to me because it's doing positive work as time goes on. I'm doing negative work. Here's one of the two formulae we're going to use for power. It's the work done by an external force in time delta t over delta t. Now, this is for a finite period of time, and so it's really the average power, and we're going to want to talk about the instantaneous power. But, if you have some force that's acting over a period of time, you just calculate how much work it did during that time and divide it by the time it took, and that would be the average power that's delivered to the system. Okay, and there was an example there, but I'm not going to go into it. Now, what I want to get to is the instantaneous power. If I have a force like my hand on this mass, and you might say, well, maybe I start out moving really slowly, and then as time goes on, I start accelerating faster and faster or something like that. The power I'm delivering to this is actually going to change as time goes on, because we already said when I'm moving it upward really slowly, I'm delivering a small power to it. The faster I move it upward, the greater the rate that power is being delivered. If I'm accelerating, then my speed is just changing all the time. And so therefore, the power is actually smaller at the beginning, then it gets bigger, and then it gets bigger. To help deal with this, we have a notion of instantaneous power, which is right now how much power is being delivered, and maybe it's changing continuously as time goes on. Here's how we might think about that. If you calculate just getting it out of the average power expression, how do we calculate the work done by a force? Well, if that force is constant, we might call it Fx delta x. And then if I associate this delta x and delta t together, delta x over delta t is the average velocity over that period of time, right? Delta x over delta t. And then if we take the limit as delta t gets smaller and smaller, that average velocity would turn into the instantaneous velocity. So this gives us a formula for the instantaneous power. The instantaneous power being delivered by a force as an object is moving along the x direction with velocity x component vx is just given by fx vx. So that means if I push harder, I'm delivering more power. But also if I push with the same amount, but the object is moving faster, I'm delivering power to it at a greater rate. So let's look at an example here. This one was in the video. There are examples of power kind of problems in the other material I emailed you today. So here's a 400 kilogram block being pulled up at a constant 2 meter per second speed by a winch. So there's a rope connected to a winch. You know, winch is something that winds up a rope and drags something, drags your truck out of a ditch or something like that. What's the power output by the winch, or equivalently by the rope force on the 400 kilogram object? Okay, to the system, well, it could be to the block, or it could be the block plus earth with gravity and internal force. It doesn't really matter. The question is, as long as I know the speed at which the object is moving and the force, force that's being exerted, we can calculate it. So let me draw a little cartoon over here since people at home can't see this anymore. 20 degrees, 400 kilograms. Doesn't look like 20 degrees, does it? 400 kilograms. I've got a rope force. Here's my winch up here, winding in the rope. And it's being raised at what rate here? 2 meters per second. And the question is, what's the power being delivered to the block, or the block plus earth, where gravity is an internal force? Doesn't matter as long as your system includes the block. What's the power that the rope force, or the winch, is delivering to the block while this is happening? It's being raised up at a constant rate. And I'm going to use that formula, Fx Vx. This is the power delivered by some force F while the object is moving velocity V. When you use this formula, the assumption, again, is always this simplified kind of situation where plus x is the direction the object is moving. If it weren't moving in the direction x, you'd have to use that more general formula, Fx Vx plus Fy Vy, similar to the other one we used. But we almost always align the x-axis with the direction it's moving. Okay. Well, I know Vx, that's 2 here, so that's easy. The only question is, what's Fx? And how do I find out what Fx is? Yeah, free body diagram for this. You got to realize this is the tension force, right? It's the x component of the tension. Hey, it's all along the x direction, so that's kind of nice. 400, I've got 400 times 9.8. Oh, this is old hat now, right? I've got a normal force. There's no friction here, right? Frictionless, yes. So I've got a tension force there. And my goal is to find that tension, and that's what I'm going to put in right here, right? It looks like it would be a good idea to take plus x going up the plane and do the sum of the force x components equals max. Ax is 0 because it's moving at constant velocity, and it looks like I have a t minus, this is 20 degrees, t minus 400 times 9.8 times the sine of 20. Okay, so t is 400 times 9.8 times the sine of 20. Okay, so essentially, this is a little bit of an add-on section at the end. The only thing you really need to know about power is 2 formulae. Instantaneous power is Fx times Vx, if something's moving in the x direction. And average power is work divided by time. And if you're using the first one, we're just thinking about work. If you can calculate the work, you can calculate the average power that happened in between the initial time and the final time. And in this case, hopefully you know something about the speed it's going at the point you're interested in it at, and you can calculate the force, the relevant force for which you're calculating the power. Whew. Okay, let's stop there. That's the end. I mean, let's not stop for the day, but I want to open it up to you guys to do practice stuff. So this is a time to do your homework, work on the homework. Think of it as office hours. I'm going to go around and help people. If there's enough common questions, we can talk about stuff up at the board. I'm happy to do that. And if you want to dig into those, if you want to take a 5-minute break, that's fine too. I know it's been a long time. If you want to dig into the old exam or those practice problems, not all of them will look familiar, but we have covered all the material that's in those. I know some of them that we just did today, we need to practice with a little bit, but for the most part, they were stuff that we've done many days ago or a few days ago. Sure. Oh, the pile driver, yeah. Well, okay, so first of all, the weight force is what? Well, it would be mg. And g is about 10, right? So the weight force by itself is about 32,000 newtons, right? Now, as it's slowing to a stop, it's accelerating upward, right? It's slowing as it goes down, which means it's accelerating upward. And that means that the upward force from this beam on the pile driver has to be even bigger than the weight force in order to get a net acceleration up, right? And therefore, you know, what do you have? Something about a factor of 10, you know, this is about 22,000. So this is about 10 times bigger than that. And that's not surprising. I mean, it's slowing down to a stop while hardly going any distance. So it seems like it's going to have a pretty big acceleration, and therefore you have put it in and it's wrong, or?
Yeah, do you think maybe I should go without the negative sign?
Well, the question is how it's phrased. Find the magnitude. Yeah, so whenever somebody's asking for the magnitude or length, the minus sign's automatically going to be wrong. But we can debug more if that doesn't work. I mean, we're talking about a huge mass that has been dropped a great distance. Now, you know, if you've got a huge I-beam and you want to jam it deep into the ground, yeah, you need something that's really massive going really fast to jam it into the ground. You can't just hit it with a hammer. It's not going to go anywhere. And so this is like a really big hammer. And yeah, the forces involved are incredibly big. But, you know, early on in the construction out there, they were putting in some beams, and they had some big, they would make a lot of noise, right? They would drop this big thing, boom, and it only goes down an inch or two, right? So you have to do it a whole bunch of times. You keep jamming it deeper into the earth. Now we're going to think of that as a work kinetic energy theorem kind of problem. Yeah. Well, I think it means what's the orbital speed. Usually when you say velocity, you mean the speed plus the direction, but I think that's just a typo there. So are you looking at this one or which one? Oh. What is the period? What's the orbital velocity? Yeah, I mean, they mean what's the orbital speed. So it just means how fast it's going. It's in a certain orbit. What's its speed with respect to the thing that it's moving around in the middle? So that's the answer to what it means. And then there's the other question of how we get to it. And in all these circular motion problems, when somebody says find a speed, I immediately think of v squared over r. That's where that v is going to appear in. How am I going to get v squared over r? Oh, I use F net equals ma components along the direction to the center of the circle, and then my a will be v squared over r, and I'm going to hope to solve for that v. So try that, see if it goes anywhere, and if you want to ask another question in a minute, raise your hand again. Yes? Okay, and let me look at my version. This is chapter 5, part 2. And what problem is it? For part 1, geosynchronous satellites. Is that the one? Okay. Yes, so what's the force acting on the satellite? And the trick, I mean, it's not really a trick. You would think that the most straightforward way to calculate the force is just using Newton's gravitational law, gm1m2 over r squared. But there's a problem you run into if you try to just calculate it directly from that. I think you're given the r, right? You're given the mass of the object, right? We know what capital G is. The problem is they didn't say it's orbiting Earth. They said that it's orbiting a planet similar to Earth, but maybe not exactly like it. So it probably doesn't have the same mass. And that's one of the things I need to put into gm1m2 over r squared. So I can't calculate it directly, and so then I'm going to have to calculate it indirectly by saying, well, I can figure out about an f sometimes by using the ma side of f net equals ma. It's a satellite, right? So it's going in a circle. Here's our planet. I'll just call it P since it's not the Earth. As it's going around, as is very common in these problems, there's only one force, and it's that gravitational force. And that's what we want to find out here, right? How big is that force that's acting on it? So let's do the usual business. Sum of the force x components equals max. There's only one force. That's what I'm trying to solve for. So it's about to tell me what that is. M times v squared over r. Now in this case, I think you're given m, right? And you're given r. How do you think we might find v?
Well, it says it's rotating so fast that it appears stationary, like it's rotating at the same speed the planet's spinning.
Right, and
It gives us the period.
it says the period is 24 hours, yes.
And it spins in one circle, and then we have the radius, so we can do 2 pi r.
Yeah. What I call it's not really a trick, but the distance over time trick, right? I would say the amount of time is the time it takes to go one revolution. That's 24 hours times 60 minutes an hour times 60 seconds a minute. That puts it in SI units. And how far does it go in that time? Well, that's the amount of time it takes to go once around the circle. So it goes to 2 pi r in that time. And you're given r. And therefore, when I calculate that, I know v as well. And that will tell me what the force is, even though I don't know the planet's mass. Okay. Yeah, I mean, so you might, or you could say, I could take x along the direction it's sliding, so in the direction down the plane, and then I would have to find the x component of the gravitational force, right? The gravitational force isn't all pointing along the x direction, it's pointing down. So you could just do fx delta x. And how far is it moving in this one? Huh, okay, maybe what's the distance it moves? Okay, so for you, it's ending up down here. This distance is 2.98. One way to do it, so let's talk about 2 different ways to do it. One way is to say, let's call this plus x. And then, since the gravitational force looks like this, say, what's your mass? 10.8. So we got a 10.8 times 9.8. And one way to do it is to say the work done by gravity is equal to Fx times delta x. So I just need, our delta x is 2.98. I just need the x component of this force, and I know how to do that. I need the angle of the plane, but we're going to do 10 times 9.8 times the sine of whatever your angle is. Here's another way to do it, just to sort of work the formulas a different way. What if I said, let's do this. Okay, well now it's not just moving along x or y, so I've got to use that more general formula, fx times delta x plus fy times delta y. Are both of these non-zero in this problem? Well, the y forces, I mean, I don't know if it's sliding down at constant speed or if it's speeding up, but in any case, they might cancel out, but that doesn't matter because we were asked for not the work done by all the forces added together, but just the work done by gravity. So I don't care if it cancels against something else. We're still concerned about the work for just this one force. So this is the gravitational force x component. What's that? That's 0. So that's kind of nice. So I only need to use this part. Now, plus y is up. So let's calculate what the gravitational force y component is. With, so this is what y means. This is the direction of that force. So I'm hoping you're okay with just, it's that thing but with a minus sign in front of it, okay? So that's this. Well, it's the y displacement only. Now it went 2.98 this way, but that's not the y displacement. The y displacement is this. And it's also negative, right? If it's going down, that's a negative y displacement. So that's going to have its own minus sign for delta y. Let's see, whatever your angle is, I'm just going to call it theta. It's going to be 2.98 times the sine of theta. Now, you see how we're going to get the same thing we did before. It's just a different way of thinking. It feels totally different, but those two minus signs cancel, and we get exactly the same ingredients in there as before. Yes. Newton's version of Kepler's third law is this. It just means g times m1 times m2 over r squared is, it's sort of like the radial component of f net equals ma when something is orbiting another thing. In this context, it will be in a circle. So it's saying, use this. Same thing we've been using over and over again. Well, so something, so let's call this capital M here, and we'll say the orbiting mass is little m, right? So let's put in some things here, right? G times capital M, that's what we're after, times little m, divided by r squared, where r is the radius of the circle, is equal to the thing that's doing the orbiting, that's little m, times v squared over r. So these little m's cancel out, but the capital M is something I can solve for in there. Yes. This is the one where someone's dragging that thing horizontally with the rope at an angle. Yes. How much work is done On the cart by the rope. Yeah, so it's going to be a positive work, right? It's moving in this direction. The rope is more or less pulling on it in the same direction it's moving, so I'm expecting a positive answer. Yes.
Okay, that's why we're finding friction, because that would be the opposite of, because if these are equal to 0, then it would be like negative.
Yes. Although for some reason, that was the way I was explaining it in the second way, but felt a little bit different than what you were doing, I
Still had to
thought.
go back and find the other two.
Yes, I don't think either way is going to be necessarily calculationally any easier than the other.
Yeah, it was kind of
You're
for that one.
yeah. Yeah, you end up having to balance some forces in the end.
So I got 16 to this one, but I don't even understand like what exactly 17 is asking. Like I don't even know how to set that up.
Okay, so this is a merry-go-round. In first part, you found the acceleration.
That's 12. This is 16.
Yeah, we're in between a page here. Okay,
Yeah.
that's what confused me.
16.
A planet. Thank you. Okay, so if an object at the equator is to have 0, okay, so that one, okay. By what factor would the speed of the object be increased when the planet is rotating at the higher speed? Okay, so now I think what we found out there is that we didn't need to use the 25 hours, but if we want to know how much has it sped up, by what factor, is the speed tripled or is it multiplied by 15, we're going to need to use that 25 hours. Okay, so, and it's by what factor the speed is increased. Is that correct, Sam?
Yeah.
So if we want to know, if I say now I'm going at 4 meters per second, and before I was going at 2, the factor we're talking about is a factor of 2, right? Or if I'm going 6 now and I was going 2 before, I would be increased by a factor of 3. So you do the later one minus later one divided by the earlier one to get the factor. So you might write it this way. The answer we're looking for is v, the speed it's moving at in the faster or weightless situation, divided by v in the slower situation. That was the 25-hour period situation. Now, in the process of doing the previous problem, did you find this speed along the way?
Yeah, we solved for
Because
T in it, so do we just substitute T back in?
you could just do the speed is 2 pi r over t. But I thought in the process of solving for t, you might have already figured out what v was. But yes, we could do 2 pi r divided by the t that you got for the first part, divided by, now whether it's moving faster or slower, notice the circumference of the circle is the same that you're going around, right? So this is t fast, and this one's t slow, which is 25 hours. Now, if I don't know if you're comfortable with just canceling those. You could invert and multiply and cancel them. In any case, this reduces to 25 hours over whatever the faster period is in hours. I'm assuming they asked for it in hours. Does that make sense? That what we want is the ratio of those speeds, because if one is 4 times as big as the other one, then the factor they're looking for is 4. So we just divide them to figure out what the factor it's increased by. It's just phrased in kind of a weird way. Are you saying come? Yes.
I feel like this one's kind of easy, but I can't figure out what to do. It's just inverse
Okay.
A cubed over t.
It sounds like it. What number is that? 5.1. Got it here somewhere. Too many worksheets. Here we go. 5 part 2, number 9. Jupiter is 5.19 or so much times farther than Earth from the sun. Find Jupiter's orbital period in Earth years. And Earth's orbital period is 1 year. Yes, so we're going to use R Jupiter cubed over T Jupiter squared equals R Earth cubed over T Earth squared. That's using Kepler's third law, which says that this ratio is the same for every planet orbiting a common mass. And in this case, Earth and Jupiter are both orbiting the same mass, the sun. So I'm assuming we're given the radius of Jupiter's orbital circle. Okay. So, well, so 5.2 times Earth's radial orbit. Okay, so let's replace that. What's being cubed here? 5.2 times R Earth. That's not the radius of Earth, but I mean the radius of Earth's orbit around the sun. Okay, let's simplify. This is going to be a year, but let's not plug anything in yet. This is going to be 5.2 cubed times the radius of Earth's orbit cubed over T Jupiter squared equals the radius of Earth's orbit cubed divided by T Earth squared. And now I can divide both sides by R Earth cubed. That's kind of nice.
That's where I went wrong. I didn't, when you separated it to 5.2 cubed and off the radius of the Earth cubed, I just did 5.2 RE cubed. And then got rid of the RE cubed.
Yeah, it's those algebra things, but you know cubed means this next to itself 3 times. So not only does the RE get multiplied together 3 times, but the 5.3 appears 3 times next to itself. That's what cubed means. Mm-hmm.
It's just the multiple choice to find the period. Like, I know the period is 3 pi over b, so I assume it's either 1 or 4, but I don't really know what g has to do with any of it.
Satellite moving. Okay, so it's very close to the surface of Earth.
Yeah.
What's the period of the satellite? Yeah, so
I would just use this, wouldn't I? Like 2 pi over b equals t.
well, but then the question is, what's V?
Yeah, v would just be. I don't know.
So we're going to get it from Newton's second law, the same thing we're doing over and over again in this homework assignment, which is, well, it's essentially up here. We've got an object that's orbiting around, in this case, Earth. Is it a satellite, right? And we know the radius of the orbit. It's R, but R Earth, whatever. And if there's only one force on it, it's the gravitational force. We usually take plus x toward the center, and here's the equation we're going to use. The sum of the force x components equals max. That's the gravitational force, which is g times the mass of the satellite times the mass of Earth divided by its radius, the radius of its circle. Now, in this case, it's right above the surface of the Earth, so its circle has radius r Earth, is equal to the mass of the thing in the free body diagram, that's the mass of the satellite, times v squared over r, and again, r is r Earth.
I'll try it, if I don't get it,
Okay. Sounds good. Hemangi and Noah, just give me a shout out if you guys want to ask questions. I'm leaving everything on just in case I hear your voice appear. Someone was raising back here, yeah. rough inclined plane. Okay, so constant speed. We're given the pulling force parallel to the incline. We're given the angle of the incline. We're given the coefficient of kinetic friction and the distance it's pulled. And find the work done by gravity in that process.
I thought this was the right way to do it. Just find that force and the distance.
And you're finding the force the old-fashioned way, just by doing a free body diagram, right? Well, now, so there's also a tension force going up the plane, right? And a friction force going down the plane, too. So I'm not sure how that plays into it, but you've got 4 forces to think about. And so in this case, you know, at least for this part, I can do it simply because I know what the weight force is. The weight force doesn't depend on any of these other 3, right? And if I want to find the work that it's done, that the weight force does, it's being pulled up the plane, correct? So is gravity doing positive or negative work, first of all? Negative work, because it's pointing more or less opposite the direction it's being pulled. And so now I could say, let's just call this plus x, and I'm going to use that fx delta x formula. In other words, if this is plus x, what's the x component of this? Well, of course, it's going to be negative, and I need to multiply by the sine of that angle, right? So it's going to be the weight force times the sine of the inclined plane angle with a minus sign, because if plus x is the direction it's moving, it's going to be a negative force. And then I would multiply that force strength times the distance it moves to get the work done by the gravitational force, Fx times delta x. For this part, I think you're going to, this is just part 1 of 3 or something like that. Right? Yeah, so you're going to have to use those other forces in other parts. But the nice thing about the gravitational force is it doesn't really depend on anything else. It doesn't matter how you're moving, which way you're moving, it's always the same magnitude. So it's the simplest thing to calculate works for.
I did everything, but I still have like the big M, and that's in none of the answers. I don't know, like, the mass
So,
of the Earth. I don't know how that just disappears.
well, so remind me what you're asked for as the answer to this problem.
Just the period T of the satellite.
The period T. So, yes.
I just need to find V.
Find V, and then you write that as 2 pi r over T, right? That's
I found that V was the square root of V times mass squared over R.
what number is this one? Let me just read the
Number
11. Yeah, okay. So consider a satellite moving near Earth. Radius of the orbit R is approximately the radius of Earth R. So if I put in the symbols they have here, they're calling this capital R and this is capital R, right? So this certainly cancels out, and one factor of this cancels out, and we want the period of the satellite, and there's no G. I know. It's because in this, so let's start over here. In this context, because you're right above the surface of the Earth, you don't have to use that complicated gravitational formula. You can just use mg, right? And that's equal to mv squared over r, because this satellite is really close to the surface of Earth, and therefore, and then, you know, put that in as 2 pi r over t, and solve for t. Yes. Which one are you looking at?
Chapter 4.2,
Okay. What number?
9.
Right. Part 1, which is number 9. Okay. What's the magnitude of the force that maintains circular motion acting on the puck? Yeah. So if I, draw, I imagine the puck's going in a circle like this, right? I always suggest drawing a free body diagram at one of the extreme, just because it'll be easier to show which way is toward the center of the circle. What are the forces acting on this puck? Well, there's that little hole in the middle, but the important thing for the puck is that there's some tension force there. There's an mg, and of course the table's pushing up with the normal force, right? And again, what were we asked for here? What is the magnitude of that force? In other words, we're asked, what's the tension? Because this force isn't doing anything to keep it in circular motion. It's perpendicular to the radial direction. Neither is this one. This is the only one that you could really credit for causing the circular motion. So the question reduces to what's T? Well, now, this is supposed to be a little frictionless hole right here, right? So that string goes through there. If it crosses a frictionless hole, that's kind of like a frictionless pulley. The tension T is the same on the bottom. Now, what's hanging down there? You're probably have a different... Now, if I hid the top of this from you and I asked, what's T? That mass is just sitting there. 9.8. It's going to balance it out because it's not accelerating. Yes.
Okay, so because it's frictionless, you can just treat it as if it were T as well, and they're the exact same.
Yeah, if there were, you could imagine if there's a lot of friction there, maybe there's a little piece of styrofoam down here, and then the tension might be very little on the bottom part. But because of so much friction, I might be pulling really hard on the top part, and it's all just because of the friction of the hole. But if it's frictionless, if they didn't balance out, the same argument I gave for the pulley is that if you have a massless frictionless pulley and you have different tensions pulling on both sides, if they don't balance out, the pulley just moves until they balance out, right? If there's an imbalance in the tensions, it has no hesitation to moving if it's massless and frictionless. So it's the same way here. Imagine this tension were really big and this tension were smaller, right? Then the big tension is going to win out and pull some of that cord up there instantaneously, essentially until they balance.
Yeah, part 2, then how would we find the linear speed? So that would just be the instantaneous velocity at one of the points.
Yes, so whenever this is in circular motion and I want to find a v. So how do we usually find a v if something's in uniform circular motion?
That's V equals RPM times PHY, or RPM.
Well, if we knew the RPMs, that would be true. But where in the physics formulae do we usually see a v appearing? V squared over r. So you're going to want to draw that circle. The tension, you already know the tension that's going towards the center, right? So do F net x equals MAX, and the AX is going to be V squared over R, and you'll solve for V.
Is our force, and then
Well, the force is the tension. So let's just draw it here. Here's the puck. I'm doing the view down from the sky, right? We know this value now. So let's do a free body diagram. I'll call this plus x. This is it. I think we're given the mass. I can't remember. Well, yeah, we're given the mass in this case. So if I do sum of the force x components equals max, well, the only force on it is all x component is t, and that's going to be equal to m times v squared over r. And you know r, you could just solve that for v. Yeah.
I wanted to ask, so whenever question asks, like, specifically about power without specifying if it's average or instantaneous, which should be assumed?
In that case, it's almost always going to be the same. it's sort of like velocity. If you might say, something was moving along. Well, if it's moving with constant velocity, the average velocity is going to be the same as the instantaneous velocity, because the instantaneous velocity won't change, and when you average it, it's just going to give you the same value. So I'm betting that that's a case where the power output is constant. If it's moving with constant velocity, yes, then the power outputs by all the forces will be constant.
The 14 when it's asking for the change of kinetic energy, isn't that just what I calculated beforehand? The work done by 147, making that extra.
Well, in this case, that's just one of many works that would be done on it, right? Gravity's doing some work on it. Tell me what number this is, just so I don't have to get close to your screen to read it. And is this chapter 6, part 1? 14. Let's see. Okay. So yes, it's pulled. We don't know it's moving at constant velocity, so it's probably accelerating, right? And you're looking at 14, right? What's the change in kinetic energy of the crate? So up above that, let's look at what you've calculated so far. What is the magnitude of the work done by the gravitational force? Now it's doing negative work, so the magnitude is positive, but if I asked for the work, it would be negative as it's accelerating upward. Yeah, okay, and that's similar to 2. And then how much work is done by the 170 Newton force? So much work. What's the change in kinetic energy? So now what that immediately makes me think of is, if somebody says change in kinetic energy, oh, if I've got a particle, the net work done on that particle from initial to final is equal to the change in the kinetic energy. So can I just calculate this? Well, let's think about the forces involved. Is there friction in this case?
Yeah.
Okay, so I've got the work done by kinetic friction. I guess in this case, since we haven't calculated this yet, this won't be the easiest way to calculate it, right? We still haven't found out anything about the work done by kinetic friction. So let's do it directly. We're given the acceleration. Your number is probably different than mine. What is it? And how far is it going up the plane? Okay. So suppose I said something, and it's starting from rest. Is that right? Oh, no, it's not starting from rest. The initial velocity is given in the diagram there, although they don't do a good job of telling you that's what it means. But it starts off with some initial velocity. So I'm just going to calculate the change in kinetic energy by 1/2 mv final squared minus 1/2 mv initial squared. We're given m. We're given v initial. I just need to figure out what v final is, and then we're done, right? Now, this sounds like kinematics. I'm given a constant acceleration, and I'm asking if it starts.
Is that number the acceleration or the initial velocity?
Well, you're given an acceleration here in. Oh.
Because in the diagram, it's just one.
Okay. Yeah. Okay. So we're not given an acceleration. We're given the initial velocity, but we would have to figure out what the acceleration is in this case. How could we figure out what the acceleration is? So my idea is we could, if we knew that acceleration, I could use our old friend, Vx final squared equals Vx initial squared plus 2ax delta x. We know delta x. If I only knew ax, I know Vx initial, I could find Vx final. And then we plug it into here and we'd be done. So how can we figure out what ax is? Yeah, so Now, I may be changing my mind again. It seemed like this was going to be straightforward, but since I don't know what, I thought we knew what AX was, but I misread it. If we don't know what AX is, it may be easier to calculate the change in kinetic energy by doing the net work done by all forces and just using the work kinetic energy theorem. So if we do the net work done by all forces, that's equal to the work done by gravity. Hey, we've already calculated that's some negative value, right? Plus the work done by whatever that force is. And you've already calculated that, I think, above, right? Plus the work done by the kinetic friction force. The only other force is the normal force. It's doing 0 work, so we don't need to worry about it, right? Okay, the sum of those three are going to be equal to the change in kinetic energy. So I've got this one. I've got this one. If I could only calculate this one, I'd get it. How can I figure out what the work done by the kinetic friction force is? Well, oh, you did? Okay.
That's what I was doing, but I said the net would be the thing that I had found above, just the tension, or
The work done by the tension?
the
Yeah.
work done.
Yeah,
So
that.
I need to add the work done by gravity.
Yeah, net means add them all up in this context. So we can't just use the tension. There are 3 different forces doing work. There are 4 forces, but the normal force doesn't do any work.
To find the net work done by the friction. First, I have to find the friction force, which would be
Mu k times the normal force.
find the normal force. I do a free body diagram.
Are we given mu? Oh yeah, we are given mu k here. Yeah.
And then I just took the weight force.
Yeah, so it's going to be the weight force times the cosine of the angle. Is that good?
Make sure I'm doing it right. It's just number 4. I'm finding the force acting on the satellite. So I'm given mass, and I use the angular speed to find the velocity, and then do v squared over r times mass. That would just give me the force, right?
Yes. So you're saying
So that's what I'm doing, and I keep getting the same.
you're just doing mv squared over r to get that force. Yes. Right.
So I don't know if I'm like converting something wrong, or
So the only thing you really have to think about is the v. Where's your calculation for v? It's 2 pi r over t.
I got 14.035.
Yeah, and that's in seconds. That looks good. You know, the other thing that might be messing us up is units. What are things
Yeah, that's
you?
what I was thinking.
So are there any other non-SI units in that problem besides the hours? Yeah. Yes, you have to switch that to meters. Meters is the SI unit. So. Natalie, how's it going? 6 part 1, it looks like. Yeah, good. You know, compared to what we were doing today, hopefully those work ones seem more straightforward, at least at the beginning. As I said, this chapter definitely is the most difficult one I feel like we do in Physics 110.
Earlier, and I got those right, but just like the force of friction and gravity, I just cannot get this.
You're asking for the work done by them. Okay, so for gravity, I mean, I think it's the cosine there. If that's the angle of your inclined plane, shouldn't it be the sine In other words, if I'm moving in that direction and I want to find the force component of gravity along this direction, the direction it's moving, I need this component of the right triangle. So I'm going to need to go across the angle, which is the sine. And then for the normal force, you do want the cosine, right? The normal force is going to be mg times the cosine of that angle. But I think for the gravitational force component along the plane direction, you're going to be multiplying by the sine of the angle. So make sure you understand that, because you want to make sure you don't make the same mistake next time. Ooh, yeah, we need to look that up. HP is horsepower. Have you ever heard of horsepower unit? It's an English. It's supposed to be how much power a horse can output. So the easiest thing to do is just Google it.
Okay.
Watts to horsepower or whatever. Did you get it in watts? Is that? Yeah. Just Google watts to horsepower. It was in, I'm sure it was in the chapter reading that you did, but I usually forget to mention it. Yes, when you get to the couple of power problems that are in there, one of them asks for a power in horsepower. Just look at it in your book or Google what the watts to horsepower conversion is. I certainly don't expect you to know it. And I'm not going to put anything in horsepower on the exam for sure. Okay, I'll go here and then there, and then back to Andre.
Like, I've had 2 people check my algebra. This same problem still not giving me, like.
It's still the one where you're dragging the thing with the angle?
I've done other problems and come back to it.
Mm-hmm.
I had 2 people say that I was doing it right and checked my work, and I just don't know.
Okay, so remind me again, we're moving at constant velocity, right? Okay, so, and your work is it 4 here? Is that the one? I mean, this is problem 4 we're talking about, right? Yes, okay.
So
T cosine that minus, this is your mu k times Fn equals 0.
And I set retention in terms of normal, and then I substituted this into here. And I solved for normal, and I was like, I solved for it again up here to make sure I got the same number twice.
But don't you want the tension?
Right, so I substitute back in.
Yeah, I mean, it's just a little bit less convoluted if instead of solving for tension here, when you do that, that means you're going to get something that only depends on normal. In other words, when you solve for this in terms of Fn and you substitute it, I get an equation that's written in terms of Fn.
So I should do it.
If you do it the other way, then you get an equation that's just in terms of t, and you don't ever have to back substitute. Now, it still should work either way. It still should, it doesn't matter which way you do it. It's just that you're solving for both variables, whereas the other way you'd only have to solve for one. If you never need the Fn, maybe you do at some other, if there's another part of the problem. Okay, so
X component of the tension that I found times the distance. So I think maybe I can back solve it and be right.
let me just check your work really quickly. Okay, so you're substituting that into your y equation here. Let me check that. Fn plus ft sine 30.1 minus mg equals 0. Looks good. And you're substituting for t in there. Where for the t?
Yes.
So it looks
I some subtract. You're right. Some of it got.
Something's
This one's more clear.
Okay.
To look at this one.
So Fn plus ft sine 30.1 minus. Okay, yes.
Fn plus the t. Yeah.
Okay, hold on. So you got a sine over cosine. So here,
Would you just make it a tangent?
well, I would just compute all three of these numbers and have it as a coefficient in front of fn. So in other words, you're going to have fn plus some number times fn. So what is that number? It's your mu k times the sine over the cosine. Because at some point, you know, you kind of get tired of carrying all these symbols around, and I'd rather just keep 3 sig figs of a number. Okay, and it's positive. So you've got one of those plus 0.3275 of them, right? So you've got 1.3275 FNs, right? You got 1 plus 0.3725, right? So you've got 1.3725 of them, and that's equal to some other number, and then you're going to divide by that 1 point whatever. Take your other number that was on the other side and divide by it, and you get an Fn. Now, does that Fn agree with what you calculated before? I'm betting the problem is like right in there then. Okay.
You can go to him first.
Okay.
Oh, I was just saying, that was the first thing. That was like the first thing I did. That was my first wrong answer. Was I tried with the sign. That's what I did originally.
Oh, okay. Well, so it seemed, but do you agree it should be the sine?
Yeah.
So this should actually be a sine instead of a cosine. So you might want to just erase it so it doesn't mess you up again. Okay. So this is an 11 kilogram mass. What's this?
That's the distance.
Oh, okay. 11 kilogram, 9.8, 7.8 meters. Is it this one here we're looking at?
No, it's this. They're like really similar.
Yeah,
Like,
they
I was
are.
able to do this one, like the whole thing, but it's just this one.
Yeah, I don't know why I put two that were almost identical, but there's lots of good stuff in this problem, so I must have been excited about it. Where's the 7? Oh, there we go. 7.5 meters. Okay. Oh, and I keep reading your 5s as 8, but as long as you can read it, that's good. Okay. That looks good. So then you're going on to calculate the work done by friction. Is this what you're getting wrong?
Well, the first one's gravity.
Oh, your gravity's not even coming out correct.
Right. Yeah, it's just those. Like I was able to get the force done by the 134. Like I was able to get this one, the work done by the puller, but and I need the gravity and the friction and the other stuff.
And you're putting it in with a minus sign, because the work is definitely negative there.
Do we put it with the line?
Yeah, I mean, unless it asks for the magnitude of the work, then that just means how big is it. But work is positive, negative, or 0, right? So.
Then I just like look back at this one, but this one says magnitude. So that makes sense.
Okay.
I was like, it must be the same. Okay.
Yeah, I don't see anything wrong as long as you're using the sign there. That looks good. Okay.
You help me set this one up because kind of like drew free body diagram right there.
Yep.
But then the 908 and confuses me.
Oh, because it's not a mass, right? I mean, you want this thing is accelerating, and so you're going to want to do F equals ma, but you don't know what m is. What you know is its weight. That number of newtons is the gravitational force. So you set.
908 is mg.
Yes.
Oh, okay.
So just solve for m, right? You divide by 9.8 or whatever their value is. Is it 9.8 in this problem? Yeah, it's 9.81. You always got to check. In different problems, sometimes they use 9.81 and sometimes 9.8. Mm-hmm.
I calculated the friction force on the friction or the work done by the friction, and then I did all the work stuff, and then I got it to be that. I solve for V final and then not V final and then plug it back in.
Okay, so is this the same one that had where you're supposed to find at some point the change in kinetic energy? Okay, and did you get that right?
No, that's what
That's what you're doing here.
I'm not sure why.
Well, so because I thought at least one way we were talking about it is we were just going to add up those three works on the left-hand side, and then that's the answer because we're asked for that. We don't need to find out what V final is because, hey, they're asking for this thing. If I can add these things up, I'm done. I don't need to figure out what V final is, at least for this part. You might need it later on. Is it just that you were entering V final and, yeah. Mm-hmm. Okay, what number is it? Yeah, that's a good method. Number 10, falling object. Okay. Well, wait a minute. Oh, you're not saying hemispherical ball. We're looking at falling object for right now, right? I thought you.
No, number 10. That's number 8.
Oh, I was looking at that 10. Okay, gotcha. Mhm. Calculate its gravitational potential energy at point A relative to point B. So that means potential energy at B minus potential energy at A. Have a good weekend. See you on Monday.
I first started thinking about like what we're thinking in terms of energy and gravity, but
Okay, so when, what they mean by at B relative to A is potential energy at position B minus potential energy at position, oh no, I'm sorry, they said A relative to B. Right? So this is another way of saying what they're looking for. Would you agree with that? How much bigger is it at A relative to B? Okay, now the distance at A above B, vertically speaking, remember we're going to use mgy, where plus y is up. One of them is a distance r above the other one, just in terms of vertical distance, right? So this is going to be, let's just write it out a little bit more. This will be mgya minus mgyb, and that can be written as mg times ya minus yb, and ya minus yb is r. So this is mgr. So we've got an m. I'd switch it to kilograms because they wanted in SI units, right? So point something kilograms, right? They're giving it in grams.
because that's what I tried to do, but I think I just put it in grams instead of kilograms. And then you basically building off of that for block C, we're going to be thinking about an increase in potential energy between B to